All right, my friends, let's take a look. For part A, since the degree of the numerator is 0, it's a constant, and the degree of the numerator is 2, I would lead you toward your arctangent rule. But our arctangent rule, instead of a 4, would need a 1, and instead of 9, would need a 1 as well. So what that leads me to do is factor out the 4/9 and then kind of go toward a U substitution technique here. So let's get started. So let's factor the 4/9 out. You'd be left with a 1 over x squared over 9 plus 1 dx. Because we're reaching for the arctangent flashcard, it would make sense to think of x squared over 9 as a quantity squared. Like that. There we go. Now from here, let's just use some U substitutions. Let's U equal x over 3, which keep in mind is just 1/3 x. So your du would be 1/3 dx, and that means your dx would be equal to 3 dus. Okay, so writing this integral in terms of u, would be left with 4/9. Let's factor this 3 out front of the integral that you'd have for the replacing the dx with 3 du. And then you'd have 1 over u squared plus 1 as your integrand, and then du on the outside. Hopefully now it's pretty clear that you have an arctangent rule. So let's multiply 4/9 times 3. You'd be left with 4/3. And then we'd have the arctangent of u, which I'm going to go ahead and just back substitute to save ourselves some writing. And then don't forget your plus c, since you didn't have bounds for that to kind of subtract out. There we go. Hopefully that makes sense, my friends. And let's kind of take a look now at part B. And you're always welcome, if that gave you a little momentum, you're always welcome to pause the video and see if you can do things that possibly couldn't do before, okay? So looking at part B, because your numerator is not a constant, I would waive that arctangent idea bye-bye for now. Instead, the degree of the numerator is 1, and the degree of the denominator is, 2 or 1 greater. And so that would lead me to think that this could be maybe like a natural log type rule. And so to that end, let's let u equal the entire denominator and see if we get away with it. All right, so if we let u equal the entire denominator, then your du would be 2x dx. And so on the top, you have 4x dx. So what I'm going to do is rewrite this integral in terms of x, and then I'll show the u substitution. So I'm going to split that 4x up. I'm going to factor a 2 out front, and then I'm going to put the other factor of 4x off to the side. And then on the bottom, I'll just copy it as is. So I'm just rearranging it so it's really clear that I'm going to put du there. And so I'd have 2 times the integral of 1 over u du. Okay. All right, let's do the antiderivative here. So we'd have 2 times the natural log. Don't forget your absolute value marks. Your u value was x squared plus 9, and then plus c. And I know I just told you not to forget the absolute value marks, but in this case, x squared plus 9 could never be negative anyway, so the absolute value marks are redundant. So it would also be correct to not have them. You always want to consider it and keep them on there if they're accomplishing anything. There you go. So in this case, you have what's called an improper integral, meaning the degree of the top is not less than the degree of the bottom. Whenever you have an improper integral, it's going to help you to write it in mixed fraction form, okay? So the most standard procedure would just be to use polynomial division. In this case, long division would make sense. Oops, sorry. There you go. Long division makes sense with spacer terms since you're not dividing by a linear term there. Anyway, so go ahead and go through the process. So let's see, x squared times 4 would be 4x squared. Make sure you distribute fully. And then subtract the whole row, and you'd be left with negative 36. And then there we've got it, mixed fraction form. So we could think of this integral as the integral of 4 minus 36 over x squared plus 9 dx. like so. And then split it into two integrals. So since integration distributes over addition and subtraction, you could think of this as 4x. And then on the second integral, here, I'll write it for a second. You could always skip a couple of these steps. I'll show them. On the second integral, you could factor the 36 and the 9 out because we're going for an arctangent now since you've got a constant over this quadratic here. So and then I hope it's okay if I skip a couple steps since this really is the integral that we did in part A. Anyway, you could use substitution over again, or you could notice that this is very repetitive from what you did for part A and possibly skip this part, depending on how observant you're feeling, I suppose. I'll go ahead and demonstrate it. There we go. So we'd end up with 4x minus 36 over 9 times 3 times the integral of 1 over u squared plus 1 du. 4x minus, okay, 12 looks like. And then you'd have arctangent of u, which let's just back substitute. Boom, and you've got it. There we go. Okay, so I wanted to make sure that I did that problem with you because you're going to be looking at examples in the textbook, and you are going to see that the textbook does inverse trig integrals, like this last one and the one in part A. They have a different method for doing those. And so it's up to you. If you want to stick with what we've been doing with this method, like I've been showing, then great. It always works and we get the same answer the book does. Or if you want to teach yourself the way that the book does it, then that's fine too, as long as you do it right, I suppose. Anyway, here's the difference. I made it so that like our flashcard rules are easier to memorize, but then we make up for it with the procedure part. But then the way the textbook does it is they have more complicated rules that you would learn, but then you have less procedure involved. So two different styles to get to the same thing. Okay, now for the rest of the examples for this lesson, and there are 6 total, we just did the first one. Because this lesson is review, I think it makes sense for me to have you kind of practice learning by reading the textbook, since I haven't done that very much for you this year. It's an important skill to have. So for examples 2 through 6, I would like for you to read the textbook introduction to section 7.1. I know some of you do this, but I know a lot of you don't. So let's give you some practice with that. I'd like for you to take notes as you read and to include all of the examples that are in the intro. So there are 6 total. We just did the first one. You should look over how the textbook does it, because the textbook does it differently, and kind of decide what you want to go with, the way I do it or the way the book does. Okay. Please do notice the textbook does have a very different way of doing inverse trig integrals than what I taught in chapter 5. Feel free to teach yourself the method the textbook uses, or just stick with the method I have emphasized. Either way, full disclosure, I just want to make sure you know that you'll see me do these problems using the method that I taught in chapter 5, as I just demonstrated in example 1. All right, my friends, when you turn in your notes, I'll expect to see example 1 that we just did together, and then examples 2 through 6 from the textbook. Okay, so that starts on page 482 in your textbook. Okay, you do not have to do the inverse trig integrals the way the textbook does unless you have decided to kind of make that switch and switch over. Each of those integrals, again, can be done just the way I did in example 1. Hopefully this makes sense, everybody. Feel free to ask me questions if anything doesn't. Take care.